What I've been showing you so far in these illustrations is that something like the cylinder that's touching the globe is only touching along one line. In other words, that cylinder is tangent to the surface of the Earth. So if this is the Earth, tangent means that it's touching like that, okay? Fair enough? So that is our, just so you make sure you see that at the bottom, that means that projections that are configured that way are using what we would call a tangent case. That's just a way of describing that type of projection. So remember, the scale factor will be 1 at the standard line. If that's the case, then how can we reduce distortion in relation to this idea of the standard line and where the developable surface touches the globe? What could we do? Let's think about that for a minute. What could we do? Let's see. We could use what's known as a secant case. If the scale factor equals 1 at the standard line, and the standard line is where the developable surface touches the globe, then why not make it so that that developable surface actually cuts through the globe? So here you can see in our planar, also known as an azimuthal projection, that now the sheet of paper actually cuts through the top of the globe. And I don't know if you can see this well, but if you were looking at this in, if that's the sheet of paper edgewise, the globe actually goes through it like that, okay? Now, what this has the result of doing or being is that before, with the planar projection, you just had the sheet of paper touching at a point. Now that we have it with a secant case where it's cutting through, that point has become a line. And what does that mean? Is that, well, if we have a line, that means that there's a larger area of our map that has no distortion because that's where the standard line is now. We've gone from a point to a line. With our cylindrical projection, our cylinder is now cutting through the globe. So again, just to make sure that's clear, if this is our cylinder, the globe is now doing this. And so we have a standard line here and a standard line there. That's what we're seeing there and there. So now we have 2 places where we have a standard line, 2 places where the scale factor equals 1 and there is no distortion. And the effect that has, of course, is that there's less distortion over our map in general, because remember, distortion increases away from the standard line. So the area between these standard lines will actually have less distortion than if you only had 1 standard line instead of 2. The same thing is true with the conic secant case. Is now the cone is touching at 2 locations, so our globe kind of does this. And so now we have 2 standard lines here. Again, same idea, scale factor equals 1, 2 standard lines. We've reduced the amount of distortion on our map. So all of this is to say that it's a strategy that's used by map makers to reduce the amount of distortion overall on a map and to make it a higher quality map as an end product. You'll often see the ones I'm most familiar with are maps of Canada, and it's the same with the US, is that they will use a conic projection and 2 standard parallels, which are standard lines, and they'll specify those, especially if it's like an old-fashioned paper map or something. And what they're telling you is where the secant case, where the developable surface is touching the globe, where there's minimal or no distortion, so that you have a sense on the map how that relates to things like the scale factor. So let's think about scale factor a little bit in relation to the secant case. Remember, with our standard line, the scale factor equals 1 where it touches. Okay, we got that. And if we think of our light bulb as being inside, this is our light bulb. I'll draw a nice little light bulb, okay? So if it's shining up like that, it's going to exaggerate things so that things are going to be larger than they really are, if you think back to Greenland again. And so that makes sense that the scale factor is going to be greater than 1 because objects will look larger than they really are. The local scale will be larger than the principal scale. That means the scale factor will be greater than 1. But what's happening here with our secant case between the standard lines is that this area, this distance, let's say, is being shrunk down to here. And so in this case, the scale factor will actually be less than 1 because you're taking objects from the reference globe and shrinking them to fit them onto our cylinder. And so now we're going to have a scale factor of less than 1. Still distortion, but it's a different kind of distortion. Instead of things looking larger than they really are, they're looking smaller than they really are. A nice way of visualizing distortion in relation to projection is to use these circles that we can put on top of our reference globe. So on the reference globe, if you imagine these as being a 3D globe with circles on top of them, and in reality these are actually meant to be infinitely small, but we'll get to that later. But you just take this idea that if you have what's on the real globe or the reference globe is a circle, and we transfer that onto our projection, we can see what happens to those circles based on the projection that we're using. Are the circles on the globe still circles on the map, or have they been shifted or distorted in some way so that their shape has changed? The circles on the reference globe are all the same size, but have they changed in size on the projection? So for example, with this one, you can see that the circles get larger as we move away from the equator. And it's kind of a way of, instead of talking about Greenland and Africa all the time, we've talked about how Greenland gets distorted so much. It's a more standardized way of trying to visualize distortion for the entire planet and say what's happening to it over all of these different regions. Are the circles larger or smaller? Are they changing in shape? Are they changing in size? So that's just a way of visualizing this. So when thinking about developable surfaces in relation to the reference globe and standard lines and how that relates to distortion, there's a rule of thumb that's often used when you're choosing a projection, and that is that we use a planar projection when making a map of the poles. We use a cylindrical projection when making a map of equatorial regions, and we use a conic type of projection when you're making a map of temperate areas or mid-latitude areas. So polar areas are planar, tropical are cylindrical, temperate areas are conic. This is just a guideline, it's just sort of something to work off of, but there's a useful underlying principle here to kind of remind us about all of the things we can talk about in terms of distortion and scale factor and so on, is really this is a strategy for minimizing distortion. Is that if you have a standard line touching near the pole, then you're going to have the least amount of distortion near the pole, so that would be good for mapping the poles. If you have standard lines between the area of the equator, then you'll have the least amount of distortion in the equatorial region, so a cylindrical projection would be good for tropical areas. If you've got a cone with two standard lines touching at the temperate areas, then you're going to have less distortion, say for a map of Canada or the US or something like that, in which case you would use a conic type of projection for temperate areas. This is not to say you can't mix and match. You can move things around, as we'll see. You can take this sheet of paper and you can have it touch at the equator. You can take the cylinder and you can turn it sideways. There's lots of different ways to do this, but this is a good starting point, especially when you're just starting out, to kind of think about this. And they are often the more common strategies that you'll see in terms of making choices about developable surfaces and areas that are being mapped. So it's a good thing to keep in mind.